Thanks, Kelly. Hey, welcome everyone. Thanks for joining to learn about statistical engineering. We have three fantastic speakers. You've hopefully read their full bios on the DataWorks website. And if not, I encourage you to do so because I will only give a very brief introduction to each one. And essentially the way the order is going to go in this session is that we'll start out with Dr. Roger Hoerl, who is going to give us an introduction to statistical engineering, followed by two awesome case studies, one by Dr. Alex Varbanov and the second by Dr. Peter Parker. And I think they will help you see how you put the concepts and methodologies, really the process and practice of statistical engineering to work, right, to make impact. And so with that, and a little bit about logistics. So each speaker is planning to speak for about 20 minutes or so. So that we have 5 to 10 minutes for questions and discussion. I will be monitoring the chat, as Kelly mentioned, and we'll ask for help from anyone else who can help to kind of monitor that chat so that we can moderate. Ideally, we'll just hold those questions, though, to the end once the speakers have completed. So with that, I'm going to turn it over to Dr. Roger Hoerl, who is currently an associate professor of statistics at Union College. Prior to that, was a leader at GE, and where I'm happy to say one of the best managers in my career. So with that, Roger, tell us about statistical engineering.
Thank you, Angie. I appreciate it. It's good to join everybody today. And just to reiterate, one of the important things Angie said is that I'm really going to be introducing the concept of statistical engineering. I'm not going to go into any specific applications. So my role is sort of tee it up for Alex and Pete. They will go through specific applications that they have personally been involved with. So what I want to do is really talk about statistical engineering, why this has become a big issue within the statistics community recently. I think most of the people, probably everybody here has a good understanding of engineering, so I don't need to talk a lot about engineering, but within the statistics community, there's been a primary focus on what I would call statistical science as opposed to statistical engineering. So I want to see if I can clarify the difference there.
Sorry to interrupt, Roger. Would you mind exiting full screen mode because the audience is seeing a small version of your slides along with the notes?
I don't mind at all.
Yeah, we're seeing your presenter view, so I think if you exit full screen, it looks the same.
Okay, so let me stop sharing and I'll reshare.
Yeah, sometimes if you go full screen before you share, it makes it better. So yeah, thank you for trying that.
Okay, is that better?
It's loading. Hold on one second.
Well, what I've got here is the outline. Due to the limited time, let me talk through the outline, and if it's still not visible after I finish, we'll do something else. I'm going to start out with a conjecture, and based on that conjecture, I'm going to share the view of someone that I have a lot of respect for, Michael Jordan, not the basketball player, but the computer scientist. Then I'm going to talk about why statistical engineering, why do we need such a thing as statistical engineering? What is it? How is it different from statistical science or what we might used to be thinking of when we think of statistics? And then a little bit about how it actually works. I'll wrap up by talking about a new professional society called the International Statistical Engineering Association, or ISEA. And you'll notice there's a ISEA logo on this presentation. The ISEA team worked together to put an introductory set of materials together, so this is not all my own work. Angie, are you able to see my presentation now?
We are not seeing it yet, Roger, so you may want to.
I'm going to stop sharing.
Try again.
And I'll try to share my screen again. Let me share my desktop, see if that makes any difference.
Yes, now that's better, Roger.
Okay, so we'll go with this. So here's the conjecture that the development of the theory and application of individual statistical methods or analytical methods, if you want to look at it more broadly, has definitely accomplished a great deal. However, when I look at it over my career, I've always felt we've sort of left a lot of money on the table, if I can use that analogy, that we haven't captured the full potential of what we could have accomplished for society. And as I've tried to think about what are we missing? What can we do better in that these tools tend to work really well when they're applied? One of the big points I think has been missed is the need to link and integrate multiple methods into an overall data-based approach to scientific inquiry, as opposed to a deep dive on individual tools. So the tools are useful, they're important, but real data-based scientific inquiry requires a lot more than just a bag full of tools. Now, this is the slide that I'm taking from Michael Jordan. If any of you are not familiar with his work, he's jointly appointed to the computer science and electrical engineering departments at Berkeley, as well as the statistics department, and is recognized globally as an authority on statistics, machine learning, and AI. In fact, in 2016, the journal Science named him the world's most influential computer scientist. And basically what he said, you can see it on the slide, that engineers pride themselves on solving problems. However, statisticians traditionally haven't really thought of themselves as being engineers and focusing on solving problems. Typically, statisticians have thought of themselves as being scientists and focus on discovering truth, whatever that means. And so what Jordan is calling on people to do is those that are applying statistics to embrace being an engineer when using statistics, as opposed to just a pure scientist, and think about statistical engineering as a counterpart to what we've traditionally viewed, which is statistical science. Personally, I think by viewing statistics from an engineering lens or an engineering viewpoint, it starts to look a lot more like other forms of engineering and less like a separate discipline that may or may not apply to engineering. So not only Jordan, but several other well-known individuals have made these same points. In the previous slide, Michael Jordan said society needs us to solve problems to carry out the statistical analog of building a bridge or electrifying a city. That is a major engineering task that goes well beyond any individual tool, and that we're often just kidding ourselves about discovering truth. Zhao Meng, who was a dean at Harvard, and now he is editor of the Harvard Data Science Journal, he developed a new course at Harvard that went along these same lines, and that this is a direct quote from him. It emphasizes deep, broad, and creative statistical thinking instead of technical problems that correspond to a recognizable textbook chapter. That is, it's not focused on the tool that we're studying right now, but it's a bigger problem that requires several tools to be integrated in order to solve it. I had the privilege a few years ago of listening to a talk by Susan Hockfield, who at the time was president of MIT. She gave a talk on the relationship between science and engineering. Basically, she talked about science developing the fundamental parts list, that is, the periodic table, the human genome, the fundamental truths of the natural world, whereas engineering figuring out how to take that parts list or the fundamental knowledge and build something of value to society, such as electrifying a city, building a bridge, and so on. So the point I'm trying to make is it's not just me that's noticed this, but other people have noticed this as well. The American Statistical Association published guidelines for undergraduate statistics programs and pointed out, I'm highlighting the emphasized part, that when undergraduate statistics majors are handed a canned data set and told to analyze it with the methods currently being studied, this can often leave them unable to solve more complex problems out of context, especially those involving large unstructured data, large unstructured problems, and that students need practice developing a unified approach to statistical analysis and integrating multiple methods in an iterative manner. So I'd argue that teaching students how to do this is a recognized need, but it's largely unmet. Hence, in my view, a lot of the people that have been trained in statistical methods don't really see how they can do this, how they can link and integrate the methods. So let's talk a little bit about what statistical engineering is. The International Statistical Engineering Association defined it this way: the discipline of statistical engineering is the study of the systematic integration of statistical concepts, methods, and tools, often with other relevant disciplines, to solve important problems sustainably. And there's a few key elements there. One is we're talking about a discipline, the study of something. We're not talking about a collection of tools. So statistical engineering is not a specific set of statistical tools. It involves integration. And of course, engineering involves integration, any type of engineering. Other relevant disciplines, those that are involved in this particular problem, which could be computer science, it could be mechanical engineering, it could be a variety of other things, to solve important problems. So as mentioned by Michael Jordan, what's different here from the way most people trained in statistics thinks is that it's oriented towards solving problems as opposed to being oriented towards specific tools. In fact, one of the terms I use is that statistical engineering is tool agnostic. It doesn't emphasize one set of tools over another, but really looks at the problem and says, what tools are actually needed to solve this particular problem? And to solve them sustainably, meaning not to win a data competition or some short-term goal, but to actually really solve a problem for the long term. And I think these provide the engineering counterpart to the fundamental tools of statistical science. Now, I'm certainly not the first person to realize that we need to build something useful from the statistical science parts list of tools. Smart people have been doing this for a long time. And as I've read some of their work and tried to figure out how they did it, what I realized is the pioneers in doing this often did it in a somewhat ad hoc manner, in the sense that they didn't document an underlying theory to how they did it. So they showed how they electrified a city or did the statistical equivalent of that, but these applications tended to be sort of one-offs, and therefore the next person that came along had to start all over again and essentially reinvent the wheel to figure out how to do it. So what we would like to do at ISEA is create an underlying theory of how this can be done. That theory then can be studied, it can be evaluated, it can be improved over time so that other people can learn how to do this a lot faster without going through a steep learning curve. So I don't claim that any of this is new, other than the desire to document an underlying theory to it and build upon what pioneers in this area have already done. Now, as we think about what it really is, one way I like to view it is what it's not. So what I have in this slide is sort of comparing what it is and what it's not. It's all about engineering solutions, hence the term statistical engineering. And of course, you don't need to engineer a solution unless the problem is large, complex, and unstructured. Easy problems, you don't really need to engineer a solution to. So it's really about engineering solutions, not about applying statistics. The statistics become tools as opposed to the objectives. It's a holistic approach because we need to solve the whole problem. It's not a purely technical approach. It's tool agnostic, as I said, rather than a recommended or desired set of tools. It's based on the scientific method, which of course is core to any type of engineering, It's not really based on writing algorithms and crunching numbers, although we may need to write some algorithms and crunch some numbers, but fundamentally we're following the scientific method. It's about viewing data as a means to an end, that is, data are how. The objective, again, is engineering a solution, solving a problem, versus viewing data as an end in itself. So it's not about data per se, it's about problems. It's neutral and broad in application area. It's not engineering statistics. That is, we can't reverse the noun and the adjective. Engineering statistics is about applying statistics in engineering, whereas statistical engineering is about engineering solutions to large problems, utilizing data along the way. Another way we might view this is that statistical engineering doesn't bring any new tools to play. It really plays an integrative role. That is, it brings tools from a variety of different disciplines shown on the right. And then on the left, it also requires the human element because, again, it's not a purely technical approach. So it studies how to incorporate collaboration, team building, the subject matter expertise from critical disciplines. How do we take all this stuff and link it and integrate it to solve a problem? That's fundamentally what engineering is all about. In this particular case, the fundamental science behind it is the statistical methods, although it borrows heavily from methods in other disciplines. Now, I'm just going to go through a couple more slides and then we'll open it up for conversation. But in statistical engineering and attacking a large, complex, unstructured problem, there's no sort of 7 easy steps. And there's no even DMAIC like in Six Sigma projects. However, there are phases of problem solving that people go through. And I think if you look at problem solving approaches from different disciplines, you'll see some similar things, although I think there are some uniquenesses here that I'm going to talk about. The phases of statistical engineering projects are, first of all, to identify the problem and really identify the right problem, not just the symptoms, but underlying root causes and across silos within the organization so that we understand the full extent of the problem. And then a lot of these large, complex, unstructured problems come to us basically as a mess, where there's a lot of issues, a lot of complaining, a lot of people unhappy with the way things are. And before you can solve a problem, of course, you have to define it. You have to provide some structure to it. You have to agree on metrics. And then you essentially have something you can actually solve. With simple problems, you can usually figure out the right tool for the right problem. But with these larger, more complex problems, you have to dig, and you're going to have to dig into the context of the problem, understand where this came from, why it hasn't been solved yet, what's been tried before, are there politics involved, personality involved, what's the history? And these are some of the things that you don't typically read about in literature in science and engineering, but is critically important to solving real problems. Most of these complex problems require us to develop a strategy to solve. That is, it's not one step, it's not one tool, but there's an overall sequence of steps, a sequence of tools that we have to apply. You're going to see this in the case studies that are about to be presented, which essentially follow this overall process. Of course, the strategy doesn't solve anything. It just gives us a path forward. Then you have to actually execute the strategy and execute tactics. Eventually, hopefully, we find a viable solution and we're able to actually deploy that within the organization, verify success, verify sustainability. And then, of course, as part of the scientific method, it never ends. There's always more problems to solve, and there's always more advancement that we can make based on what we've already done. I should also point out, I'm depicting this in a linear fashion. Of course, it doesn't work in a linear way. There's a lot of feedback loops, but it becomes pretty complicated to try to show that. Now, these three phases in particular: provide structure, understand context, and develop a strategy. These are the phases that I think all too often are ignored in the literature. There isn't a lot of discussion about how to provide structure, how to understand context, and things like that. So these are the areas that I think we need a lot more emphasis on. Now, in the interest of time, I'm just going to skip over these. Everybody will have the ability to see these, but what I want to do is talk just for a minute about the International Statistical Engineering Association. Here's the website. There is a handbook being developed, and it's actually about 80% done. It's up and available for members. It is free to join ISEA. There's about 320 members as of today. So if anybody is interested in looking into this further, especially after the talks that are coming, feel free to go to this website and you can join for free. So at this point, I'm going to stop sharing and I'm going to go back to Angie and see if there's any questions that people would like to ask. Angie, you are muted.
There we go. Can you hear me? You can hear me? All right. Okay, great. So I think, so we had one comment in the chat. Otherwise, I would encourage you to, anyone who has a question, pop it into the chat or raise your hand so that if you want to actually ask it verbally. So one question early on by Kirsten, I think when you started out, Roger, was, and this is kind of talking about more the education, the preparation, right?
Yep.
So should we consider maybe recruiting more physicists that are trained in probabilistic math and problem solving? And maybe you can answer that and expand a little bit more on what is the right kind of educational foundation?
Sure. First of all, I absolutely agree with the comment. And I can honestly say some of my best friends are physicists. And Angie remembers a physicist we work with quite a bit at GE Global Research named Dick Mesmer, who knew a lot about probability and a lot about solving problems in statistics. So I absolutely think you're right. One of the things we're trying to do, and one of the reasons we're here at DataWorks, is we do want this to be a cross-disciplinary effort. And physicists, of course, are trained, as you said, in probabilistic math and problem solving. And as we know, there's a lot of physicists on Wall Street doing financial analysis. There are a lot of physicists that have a business card today that says data scientist. So I would love to get more physicists involved. I think they can contribute quite a bit. And my long-term goal is that professional statisticians would be an important but fairly small percentage of the membership of ISEA.
Great, thanks, Roger. Let's see, anyone else? Not seeing any other questions. Oh, here we go. So we have a question from Michelle.
Yeah.
So when you say tool agnostic, do you mean that there are no currently developed tools for certain types of engineering problems, or that there should never be tools developed?
Okay. No, I definitely think there should be tools developed. I'm all in favor of tools. In my experience over my career, I've seen professionals, statisticians mostly, but we could throw in engineers, mathematicians, others, where there's a dogmatic loyalty to a specific set of tools. So for example, in statistics, you have a community of people that would identify as Bayesian statisticians and another group that would identify as frequentist statisticians. And a lot of times the frequentists don't like the Bayesians don't like the frequentists. They get into big arguments at conferences. And I think it misses the whole point. The whole point is we shouldn't start with the best set of tools and figure out how do I apply Bayesian tools or frequentist tools. I think that's the wrong question. The right question is, given the nature of this particular problem, what tools would be most useful for this problem? And you know what? If it's a Bayesian method, let's use it. If it's a frequentist method, let's use it. But I would like to see professionals get away from, well, I'm in this camp and I promote this set of tools, to focused on the problem and figuring out which tools are most appropriate for this particular problem. That's my fundamental point, that we have loyalty to solving the problem, not loyalty to a pre-selected set of tools that I happen to like.
Great, thanks, Roger. So I'm going to take these questions in order, and we have time for at least a couple.
Yep.
I think. So this one is from Paul. And the question is, how does this compare with the various consulting approaches, such as the Shannon approaches?
Well, I'm going to, if you don't mind, I'm going to join John's question with Paul's.
Okay.
John asked a
absolutely.
similar question about machine learning and AI. And since I'm running out of time, I'm going to try to
Okay, Roger, go for it.
handle both of them. Since we started this discussion of statistical engineering, there's a similar question to these that I've been asked frequently, and it's taken different flavors. So for example, within the statistics community, people have said, well, isn't what you're talking about just the same thing as applied statistics? And within the machine learning community, people have said, well, isn't what you're talking about the same thing as machine learning? Or isn't it the same thing as industrial engineering? Or isn't it the same thing as data science? And where I'm coming out on this is, I don't care what you call it. So you can call it applied statistics, machine learning, data science, whatever you want to call it, as long as you're doing these things. Now, in my experience, many of these disciplines haven't spent enough time carefully documenting problems and ensuring that they're working on the right problem, that they've properly structured the problem and evaluated the data. And if you look at things like Kaggle competitions, for example, there's a very narrowly defined criteria, like out of sample root mean square error, that defines the best model. But best for what? I mean, is anybody really going to use that model to solve a problem? In the Netflix competition, for example, a team from Bell Communications Research won $1 million prize for developing the best model to predict how people would rate Netflix movies. But Netflix never actually implemented the model. It never went into production because it was too complex. It involved 107 individual models. It was an ensemble model built on those. And so it was never actually used. So as long as you're doing the things that we're talking about, using the scientific method, using a formal problem solving structure, being tool agnostic, I don't care what you call it. But I'm a professional statistician. I would say that's not the modus operandi of the statistics profession, which tends to focus on tools. And so I would like to see some change, but feel free to call it whatever you call it, as long as you're doing the things that we're talking about that I think relate to getting good solutions.
Great, thanks, Roger. So I don't know if you could see there's maybe one more question in the chat. I don't know if you feel like it's a quick, you can wrap that up.
Yeah, I will. The question was, because there's the dimensions of possible solutions outweighs the knowledge of any person in group, is there any such thing as best? Is that a loaded question? Yeah, it is. You're right. However, we got to do something. So among the options that we have considered and looked at, this one appears to be the best of the lot. Is it a global optimum? Probably not, to your point. But we have to do something. So let's look at the options we can think of, the options we've evaluated, and which of these seems most promising of the ones that we've considered. That's the sense in which I meant it.
Great. Hey, Roger, thanks so much. And everyone, you can give your silent round of applause for Roger. We very much appreciate your time. And with that, what we like to do is move on to the first of our two case studies. The first one being presented by Dr. Alex Varbanov, who is a principal scientist at Procter & Gamble, where he's been providing statistical leadership for 21 years. So Alex, I'm going to turn it over to you. Thank you.
Thanks, Angie. Do you see my first slide?
Yes, I can see it.
Okay, thank you. All right, thanks, Angie, for the introduction, and thank you for the organizers of the session for the invitation. I'm going to talk about a competitive laundry initiative. This presentation that I'm presenting also on behalf of my co-workers, Sonia Escobar and Cindy Rodenberg. Three of us work for the Procter & Gamble company. So I joined the team 2016. At the time, I didn't really know what statistical engineering was. Since then, there was several presentations and workshops organized at P&G with external experts. So I think I have much better understanding now. And I think this fits into a case study for statistical engineering. It's rather simple kind of example. Definitely, there are a lot more complicated examples, but I think it fits well for something that we can present here for 20, 25 minutes. So this is what I'm going to talk about. First, I'll give you some project background and the business impact that this project has. Then I'll talk about link to the statistical engineering, and I'll cover the 6 statistical engineering stages that Roger talked about, introduced, and then I'll finish with the summary. I'll start with the P&G mission. Probably you know that P&G is one of the top 10 largest consumer packaging good companies in the world. There is a big R&D department, and one of the main responsibilities to innovate and develop new products across different categories. When we do that, we always have to keep the P&G mission in mind, in particular that the consumer is in the center stage. And when we produce new products, we need to illustrate superior quality of the products relative to competitors. So in order to do that in the laundry area where I provide statistical support in, we have started this initiative a few years ago. Fabric and home care is one of the P&G 6 industry-based sector units, business units. Actually, is the biggest one. There are a lot of competitors that play in the area of laundry business. Henkel and Unilever are key competitors, and there are also several private label brands, or what we call them also store brands. Let's say Kirkland, for example, is the Costco brand. When we talk about the laundry initiative and the laundry business in general, there are several benefits that the laundry provides. The ones that we focus in this initiative, and the key ones are stain removal, malodor removal, whitening, color care, and freshness. So as part of this initiative, we collect a lot of data that inform us about those benefits. This slide is a little old. I created it a few months ago for another presentation, so the number has grown up, but we have at least 800 products. Yeah, you could be surprised that there's so many detergent products. I'm even talking North America. But there are a lot of variations. Of course, this is over the years, so there is repetitive formulations over the years. But we have a lot of stain removal outputs, malodor and freshness screenings, and readings about the other benefits as well. And this is growing with time. So before I go into more details about this project, just why is this so important to us? There are several critical benefits or value that it adds. On the left-hand side, you see shelf. That's meant to represent that in order to sell product, they have to appear on the retailer shelf. And it's not that easy to appear because there's a lot of competition of products. So you have to convince retailers that your products are really superior and will be selling well. So it helps in our communication with retailers. On the bottom side, the histogram is meant to represent that once you collect data on a kind of critical key major players on the market, you can understand the whole distribution of performance, a particular performance measure, and you can start making claims as the one we made, like Tide #1 stain and odor removal brand. And there are some other benefits, but I'll go on with the next thing I want to talk about is this program provides a competitive advantage to us. Key components of it is having the right data foundation, a multidisciplinary team that I'll talk about in a minute here, and also strong relationship between the business unit and the corporate function there, where the statistical group is located. And what it ties together, really, those three major components is the statistical engineering and its framework. So why this project relates to the statistical engineering? I think it's multidimensional on several levels. So first, there are lots of data that's dispersed across multiple studies. So we have to integrate information across studies and products. Also, it's a multidisciplinary team is involved. You need to have a product researcher, statistician, and so on. Also, multiple benefits and then multiple customers. You can have a retailer, sales teams, you can have product researchers, or you can have other groups that benefit from this project and this program. Because there are multiple data sources, there are multiple data challenges when you integrate the information. I'll talk about lack of standardization that we had initially and how we handle it. There is also statistical complexity when you integrate different data sources across studies. How do you integrate it so you preserve the variability across tests and don't underestimate uncertainty? And then since it's multidimensional on several levels and essentially different moving parts that needs to be coordinated, you need to think about the strategy, where to start, how do you structure the data, the problem, what are the outputs, and how do you get there? So I'll talk about these 6 stages and how it links to our projects, to our project. A nice paper that discusses those is listed at the bottom here. It was very nice intro to the area that I benefited personally from to get better understanding of statistical engineering. So let me cover each one of those areas and how it links to our project. I'll start with the first one. So identify the high impact problems. For us, this is which are the key questions that we need to answer and show that these questions are really important for the business. We can group those questions in kind of 4 groups. The first one, status quo, that's about benchmarking. So where is our current products relative to the competition in among all the benefit spaces that we measure? The second group of questions it's about intervention or investment. So where how have other products changed over time, and is it time for an intervention on our side? As you involved in product development, you know that there is a cycle of sometimes you focus on superiority and you invest in new products and better products. Other times it's a cycle goes into cost saving. So you try to reduce the cost of breaking a product and trying to preserve as much as possible the performance. So depending on where this cycle is, you might have to think about the investment, especially if competitors have improved their products recently. The fourth set is about the third set of questions is about the consumer. As I mentioned, she's a critical part when we develop products to have in mind. And also when we develop superior products, how do we communicate in a proper way the benefits of the products relative to the other products in the market? Could be really very overwhelming for a consumer when it goes into a store and there are a lot of products on the market. And then the last thing is about expansion, or how do we kind of cover white space area and develop products where we currently might not have, anyone might not have good presence. The second thing is about providing a structure. There are two kind of things I want to talk about here. One is the team, providing team structure, and then the other one is providing product annotation structure. I'll start with the team. So we had relatively small teams. I personally think small teams work better than big teams as long as they cover the necessary expertise. And one of the good things working for a big company like Procter & Gamble is you can easily form a team of experts from different area because of the size of the company. So in this particular case, we have a team of 5 people. The project leader is also the project researcher. She had very good understanding of the product category, and she has chemistry, engineering background. Lab researcher is the person who gets the studies to collect the data. Statistician, that's my role. It's involved in all of the spectrum of the statistical work, from study designing to data processing, analysis, results interpretation, all the typical statistical tasks. We have also informatist. I'm not sure if this is kind of a common name externally, but what that role is about is how do we develop tools to access the database of results. So it's creating a web interface and make it easy for users to access the results. And then the last role is the manager role. Providing structure, early on we realized, because we collect a lot of data, different teams are involved in measurement, analytical sensory panels, image analysis. So we realized that there wasn't really a good structure in the beginning of how we can keep track of the different products. Company brand and form, those are easy, but there are so many variations of product and scent that we have in the laundry business that we need to establish like common product annotation, hierarchy, and follow it strictly with corresponding IDs so that we can track when product appears in multiple studies or when we want to link data for the same products across multiple benefits. The third step or stage, statistical engineering stage, and as Roger mentioned, we are listing them sequentially, but there is a lot of iterations and connection. The order is not necessarily always like that. But the third stage I want to talk about is understand the context. For us, this was identify plan against the critical challenges. The first one is working in highly focused organizations. If you work in an industry, you probably know this, that there is always the balance between winning now and delivering now, and also making sure we're going to win tomorrow as well. And usually in that kind of balance, it's biased naturally towards winning today. And this program that we have been trying to establish is more of it requires some overhead in the beginning, collecting some data before you can start getting value out of it. So we had to deal with that kind of a barrier to communicate the need to invest into to get the results later. The second thing is there is uncertainty in committing to future value initiatives that involve high initial cost investment. So we had to be here creative in a good sense of the word to create test methods that are efficient, that we can cover more products, split across multiple tests. Also, how do we integrate the information in a way, the statistical methods that are proper for integrating information across multiple studies. And the last point here is about being able to work with this constant reality in the industry that we always want to do more with less. That I think managers came up with that thing, but it's always how you have to work in the industry under that pressure. The next stage is to develop strategy. There are 4 critical things that I would like to mention. First thing is the data standardization. I kind of covered this with the product annotation hierarchy. But overall, it's unless you organize and get very digitized there are a lot of data coming through different Excel files, different sources, and it causes difficult and time to process the data. So the more you organize on this end, the better, the easier it becomes. Data quality using validated technical methods. So we make sure we get good validated technical methods to get good results. If you don't have good test methods, you can get very noisy results and it's not going to be useful. I want to spend a little bit more time on third and fourth bullet points here. So we have been using statistical thinking during the study planning. If you're a statistician by background, you're familiar well with those topics covered in a typical experimental design course. So randomization, controls, blocking, replication. So those are critical concepts and things we used when we were planning the studies. On the statistical analysis part, we're using the network method analysis approach outlined in the paper referenced at the bottom here. If you're not familiar with network meta-analysis, it's a nice way to integrate information across studies where the studies are really incomplete blocks. So you have only a subset of the products in each study. As long as you have sufficient overlap of products across studies, you can apply this network meta-analysis approach, which preserves also the heterogeneity across studies. So it's kind of conservative in terms you don't underestimate uncertainty when you compare products from different studies. The next thing is develop and execute tactics. So there are many tactical decisions that enable the project. I'm going to talk only about four of those. We use pilot studies to validate new technical methods. So before we start generating a lot of data for a technical method, let's say stain removal technical method, we use pilot studies. We explore different sources of variability. We make sure we can either reduce variability or we can control in a way that we can design studies so that it's the variability is not confounded with the treatment comparisons. The second point is it's very critical to have repeated controls in these studies tests so that we can integrate information across tests. Without that, it's just a disjoint set of tests and you cannot account for test-to-test variability. We use SAS software for all data processing, analysis, and activation. Doesn't have to be SAS, it could be R, but just the skills in our group were matching best using SAS in this case. And then we provide access to the product result using an online access tool, which brings me to my next point here, which is the identify and deploy final solution. So the final solution consists of two components. One is the database of the results. So we apply network meta-analysis. Once we get new data, we update the statistical summaries for different products across different benefits. And this database of results is the one key component of the final solution. Now, to access this final solution or this database, we have created what we call Web2, which is an intranet web page that allows the user to specify a few products at a time. Then that information is sent to a statistical server where which accesses the databases and extracts the information about the selected products and provide it back to the user in a standardized format. The nice thing about having it set up like that is we can update the databases in the background without interrupting the usage, the process for the user to access the results. And this is my last slide here, this is my summary slide. P&G Competitive Product Laundry Initiative is complex. It covers multiple benefit studies, products. We cover more than, I think it's right now, more than even 1,000 products over 5-6 years. The bottom line is it provides us with uninformed data-driven business decisions. It's a support for those decisions. I talked about how it links to different statistical engineering elements, and I think it fits well as a simple case study to illustrate how statistical engineering can help a business problem like this one. That's all I have. I think we have some time for questions.
Yes, thank you, Alex. So again, this is Angie, and I would encourage you to post your questions in the chat or raise your hand if you'd like to ask them directly to Alex. I think while we are waiting to see if people post questions, Alex, I'll ask you one. So, you walked us through really the 7 kind of phases or stages as Roger described them, right, of statistical engineering. So for this initiative for P&G, maybe could you tell us of the stages, what did you all find? What did the team maybe find the most challenging, or what aspects of kind of a statistical engineering approach or process did you find the most challenging, and how you were able to overcome those?
I'll give my answer. I'm not sure if the product researcher necessarily would give the same, but since I'm biased more toward the data processing integration, the standardization and the access of the data, I think was kind of one of the challenges, at least in the beginning, because different people were naming same product differently. Even if same person, we give them to do a test over time, they might not necessarily call them the same. There are a lot of product variations and stuff. So keeping this track, in the beginning, we did not realize we have this. We realized we have this problem. We didn't have a quick solution. So we had to involve in a lot of manual work to do the matching after that. But once we set up the framework of the annotation, we make sure every person who runs the test follows that. It was easy after that. So that was my part. I think communicating the results in different with different people, you have to do different depending on what their objective is. But that was more on the product researcher side and their responsibility. I'm sure there are other challenges that I mentioned are also important as well. I think making sure the business to understand that requires an investment, and then the results are coming after that. That was a challenge too.
Certainly, thank you. Anyone else? Questions or discussion?
Well, people are thinking about questions. I just want to mention that I think statistical engineering is not, as we know, it's not something that has been taught at school. So a lot of the stuff we had to, I realized I learned in practice. So I don't know, I have worked only for one company, P&G, for 21 years. So maybe I was lucky. There are different programs that and short courses that have helped me, I think now, then I think in the perspective to kind of apply some of the statistical engineering concepts. But yeah, I think it would be nice probably to have a course like that for students who graduate and want to go and work in the industry. Definitely would help them. And we see more and more problems that fall into the statistical engineering category these days, especially with so many different data sources available. And we talk more and more about data integration. I think those becomes more the standard now than the exception these days, I think.
All right, thank you. Yeah, and we had the comment from Kirsten. Again, I think, like we said previously, physicists perhaps are, by training, get that blend of methods and problem solving skill sets. And perhaps we're also looking at how in addition to the physicists, right? How do we give engineers that a capability to have maybe the stronger data analytic skills, kind of being able to take those problems and map them to problems that can be informed by data, as probably physicists already sort of trained to do. And with the statisticians, or people who are more purely trained in statistics or data science, having that problem solving skill set, being able to map. So we have a question from Christine. It says, connecting to a previous question, how did you gain confidence that you had found a best solution that was right for P&G?
Okay, that's a good question. So I think it's important. It's not that one person. It's a team that has been involved in this. So we have been having discussions along the line. When we have different routes we can take, which one makes sense. Obviously, the person with the most expertise, if it's about statistical question, the way that brings the statistician is more important. But through communication, I think it's important. Statistical engineering problems are not solved by one person, they're solved by teams. So by having open dialogue, by having good experts on the team to make sure they represent well the corresponding discipline, it's how I think things are get done. You have to balance what's also feasible and practical. There might be great solution, but it's not feasible within the cost constraint you have. So when you work in the industry, practical matters as well. But through dialogue, through exploring alternatives and trying to find the best methods externally, as any other probably approach, that's what we took.
So Alex, we have a question from Paul. How do you deal with management's push for Six Sigma?
For me, Six Sigma is about making sure you provide quality of data. Actually, it's for us, it's up to the statistical expert more to push for the quality of data than the managers. I think it's falls kind of in our responsibility. In our particular case, we make sure we have validated test methods. So we kind of have methods that provide uncertainty that we can measure it well, we can understand it, we can control it to the extent we can, and make sure when we analyze the data, this is taken into account. So by controlling the quality of the data we generate, that's how I, if I understood the question correctly, but the management will push for a lot of things. We try to do our job the best we can to collect the best data we can. So we apply the principle as well. Hopefully I answered the question.
So just if you want to comment, and I don't know if this is the culture at P&G. The question is about kind of Six Sigma as a religion. I don't know if that's a push at P&G, but if so.
It's having data quality, it's important for P&G, but the Six Sigma as a religion, it's not the reality at P&G in terms of blindly following it.
Okay. All right. Alex, thank you so much for sharing the case study with us. And I'll do the applause since everyone is on mute. We thank you again for your time. And then at this time, we will move on to our second case study, which is going to be presented by Dr. Peter Parker, who is a team leader at NASA's Langley Research Center. And he serves there as an agency-wide statistical expert across all of the mission directorates to really drive statistical thinking, engineering, and methods. And with that, I'm going to turn it over to you, Pete. Thank you.
All right, well, thank you. Thank you to the DataWorks organizers and Angie for moderating this session. And We've had two great talks to start off with. Appreciate Roger and Alex. And so I'm going to talk about a case study involving a space launch system. This particular case study involves taking heritage architecture from the space shuttle, one of the reusable solid rocket motors that was flown as part of the space shuttle system, and using it in a single rocket, single stick configuration, a concept vehicle that was known as Ares-1. And in order to do that, there was some testing done. And in that testing, the rocket engine is laid on its side. It's bolted to the ground, bolted to a measurement system, and it goes through a full-scale firing. The picture there in the middle with that plume of flames coming out is a picture taken from that test stand in Promontory Point, Utah. And then I'm going to talk a little bit.
Pete,
Yeah.
I just want, sorry for the interruption. The slide did not advance for me, so I'm still seeing your title slide. I don't know if that's true for others as well. There we go. There we go. And now I see the second slide.
Okay, we'll go with this view. This worked for Roger, it'll work for me.
Thank you.
Okay, so we're taking this reusable solid rocket motor from the shuttle, using it in a different configuration to leverage heritage architecture. And as I was saying, the picture there in the middle is of that engine bolted on its side, bolted to a measurement system, and fired through its full-scale firing. And as I tell this story, I have a nice bookend, which is an actual flight test and the result of that flight test. Now, this is going to be a retrospective look back across the project. And I'm not going to go into a lot of the statistical details. What I want to focus on in this discussion is on the problem-solving techniques that were used. For a military language, I think, and it might be called an after-action review. And one of those things that's important is not only to talk about what we did well, but what we could have done better. This is a real case study, meaning it's not a perfect textbook example. And another component of that after-action review, as I understand it, is external perspectives, not just the leader's perspective on what went well and what didn't go well. And so I'll ask you as you listen, please take note on things you think went well or things we could have done better, and maybe we'll have that discussion for the Q&A. So in the upper left corner, I've tried to identify the different phases of statistical engineering that are being used. And, it's not quite so nice to fit into a pigeonhole, but I've done a best chance at trying to identify that. And so I want to start off, and I'm going to spend quite a bit of time in the beginning here, identifying the problem, understanding the context, because those are particularly important and a focus of statistical engineering, a unique focus compared to just the solution approach. And so the background is, as I've said, leveraging heritage architecture. And why do that? Well, to minimize technical risk, cost, schedule. However, those components were subject to new requirements that weren't part of the original system, and they were never tested. So the test and evaluation capabilities weren't present to do that. In particular, the component, and I probably skipped this through our fiddling with the slides there on step 2, is a component called roll torque. And that torque is, imagine that single rocket going through a rifling type of motion as it takes off. That wasn't important in the shuttle system, where you had two engines bolted on to a main engine, but in a single configuration, it was very important to characterize. And so that's really, now that we're back on track from that picture, that's what the main topic here, we're going to hear you, you hear me talking about roll torque. The vehicle itself, the Ares-1, was predicted to be overweight, and the system was scrutinized and looked for the largest uncertainty or the components with the largest design margin. I'll talk more about how important weight or mass is to a vehicle, to especially a launch vehicle on the next slide. And so this roll torque reaction control system, the system that's put on board to react and to keep the rocket from doing this rifling type motion during flight, was considered to have high uncertainty in its requirements. It lacked adequate test data. It lacked a physical fundamental understanding. and therefore it was a good candidate to be considered that it may be being over-designed, resulting in excess weight on the vehicle. So the simple kind of question of this whole project is, how large does that reaction control system need to be? In flight, space flight systems, we say mass is king. Mass affects all payload and mission capability. Essentially, the heavier the vehicle, the less science, the less interesting things that you can carry. And more importantly, excess mass in a complex system like this becomes a life cycle cost. Once it gets on board, it's hard to get that mass back off. Now, that's one of the consequences. Obviously, insufficient control authority of the vehicle would result in unstable flight. And there's lots of follow-on consequences for that. Potential loss of vehicle, loss of payload if it's unmanned, and loss of crew if astronauts on board. So this is a problem that falls into this category of very high consequences for the organization and for the spaceflight system itself. Now, as you might imagine, there were various players involved in the context. And I think Roger alluded to this that often when we start with these problems, we start with a bit of a mess. In this case, there were previous firings that were unsuccessful. They were unsuccessful in obtaining, and we'll just put it in quotes, high confidence measurements. And it really was unclear on the part of the team what we should try to do next. I thought of it as two different options. One, we could try to increase our confidence in our existing data, or two, develop a new strategy for testing. As the system became more of a focus, NASA's independent technical authority, known as the NASA Engineering Safety Center, who reports directly to the NASA chief engineer, became involved. And culturally, there was very little experience with statistical design of experiments. And you're going to hear that in my talk, and I'm not going to focus this talk on statistical design of experiments, but I think many people in this venue are very familiar with that. And there was very little experience in comfort. Comfort might be a nice way to say that there were some bad experiences, little comfort from some bad experiences. So we had multiple organizations involved: the program, who was developing the system, the independent technical authority, and our partners, our contract partners, who were developing and testing the system. The system was critical in safety in terms of the facility itself, and I'll just talk about that for a minute. The test facility, the personnel, the high-value assets of that test. That's a full-scale solid rocket motor that's being tested. And so I think it would go without saying that this falls into the category of that large, complex challenge of a statistical engineering problem. And at the time, it doesn't hurt to say that it was the most powerful solid rocket motor in the world that we were about to test. So as we start talking about providing a structure, it was clear that it was going to require a team, an interdisciplinary team. There was incomplete knowledge on the original design, and that was specific to this component that was never part of the shuttle system, the internal roll torque of that rocket. So there was no single expert to ask, and the multiple disciplines as we started had disagreements about what this roll torque value could be. And I'm going to show a chart here in a few slides to show you numerically how much that disagreed. But it came from first principles, it came from scaling other vehicles, came from computational analyses, modeling and simulation, and they all didn't agree. So that interdisciplinary team was formed, and I'm not going to read that list that you see on the screen. But at the very bottom, there was statisticians added to that team. And you might ask, well, how did the statisticians get invited to the team? Well, they weren't. That's the short answer and one of the lessons learned. Early in my career, I had developed experience and expertise in force measurement systems. That's how I got on the team. And what I brought along was my experience and knowledge of industrial statistical products, processes, like design of experiments. I think this is a really good lesson learned. And I think particularly for this DataWorks community, where we have a lot of deep subject matter experts who have the ability to sit at the table and bring these statistical thinking, statistical tools, statistical engineering perspective to the problem solving. And one of the lessons learned, and I'll talk about it later, is in the future, statisticians were invited to the team. The initial problem was to measure this internal roll torque, and that sounds simple enough, but I think many of you would agree that such a simple question probably has a lot of details, and it was too broad. We accepted it, and we put most of our focus on getting the data. The precise problem definition of exactly how that measurement was going to be used in subsequent modeling and simulation was not an initial focus. And so it turned out we did measure roll torque well, but we didn't do it under the most relevant conditions. And one of the lessons learned is that we should have asked more questions. We should have pressed for a clear understanding of exactly how that measurement was going to be used. And in the yellow box, I say, we felt that they knew what they wanted. And so we worked hard at what we knew how to solve best, which was to go get the data. And this is definitely stepping out of your comfort zone for a lot of people, but this is at the core of statistical engineering, is taking this time up front, the discipline, to define the right questions in an unequivocal way, in a measurable way. And that's definitely a lesson learned here. So now I want to talk a little bit about that structure from a quantitative perspective. These were, the chart shows the roll torque on the y-axis, and it's in thousands of inch-pounds. You can sort of forget the units for the point of this talk. And you see those values range from about 0 up to a little over 200. All of these are different ways that that roll torque had been estimated before we got involved. And they involved previous experimental data, some innovative techniques. One was to measure the plume at the back of the rocket, the swirling motion, and to be able to detect how much torque may have been involved to create that swirl from analyzing the video. As you can see across, there was a large range of estimates, and there was no consensus across the disciplines, and there was no uncertainty on these estimates, and that's a very important aspect. You know, my background is engineering. My undergraduate degree is in engineering, and I know that when asked a question about a parameter, an engineer gives a value, and they internally sort of figure some uncertainty on that value, but not expressing it explicitly makes it very difficult to communicate across disciplines and to come to some consensus. The design requirement was set at 200,000 inch-pounds, sort of near the max. The experimental plan involved a nesting and sequencing of multiple design and analysis phases. It involved characterizing the facility, first of all, which involved applying loads to that test facility that would simulate the loads that would be generated during the firing. Then the firing itself, the 120 seconds of the burn, the nozzle was vectored in different directions, and that in and of itself is a design activity. How are you going to spend those precious 120 seconds to get the information you want? In step 3, we had to combine those models and add uncertainty and communicate what that uncertainty represents. And in step 5, there was a lot of time spent with subject matter experts to talk about how to come to a consensus estimate on that uncertainty, to understand the measurement that was being delivered and what it was going to be used for. Ultimately, the deliverables from this fed, as I said, a modeling and simulation, a guidance, navigation, and control flight simulation. So it was a strategy of sequencing, integrating, and extending existing methods. I'm going to briefly go over some of these methods, and as I said in the beginning, I'm not going to focus on them, but if you want to know more, please feel free to reach out and contact me. In terms of the facility characterization, we applied factorial combinations of loads. We were unable to apply pure replicates. We were under restricted randomization. The weight of the rocket, the propellant, is what created a significant effect on the measurement system. So we did this characterization before and after the burning, which resulted in non-replicated hole plots. It's a destructive test. Once that propellant is gone, you can't put it back in. It required an adaptive response surface we adapted a response surface methodology to have a 5-dimensional second-order response surface for five individual responses. And that required inverse prediction, a calibration type problem, with estimated uncertainty. And to put a little icing on the cake, we couldn't apply all of the loads and all of the combinations, which restricted our ability to fully characterize the system. Now, one more slide on that response surface adaptation. You know, if you're familiar with response surface methodology, you know that it's often used for product and process optimization. Well, we were using it for characterization, where the mathematical model was the product, not an optimized setting of factors. And we wanted confirmation points over the entire design space, not just in one local optimum. I mentioned this inverse prediction, and I put one equation here. This is the one equation basically in the whole talk, where this is the type of calibration problem where you need to predict the X's from a collection of Y's. If you look that up in a statistical textbook, you'll see simple linear regression. That's the most that you often will see, not a 5-dimensional second-order response surface. So we had to come up with some innovative techniques and solutions in order to provide uncertainty on that prediction. An iterative solution, by the way. This is the firing duty cycle of the rocket. As I mentioned, the nozzle is vectored during the firing, and this plot shows the different positions in which it's vectored through to test a variety of measurements and systems on the vehicle. I want to direct your attention to the 5 locations where there are circles. Those are the areas in which the nozzle passed through 0 degrees, meaning the nozzle was collinear or aligned with the main axis of the rocket. Those are the points where we wanted to measure roll torque. Those 5 points provided what the metric, the measurement location that was of interest for guidance, navigation, and control. This is a plot of the results. The measured or predicted roll torque on the y-axis. The center line is the mean, and you'll see intervals, upper and lower intervals. First thing to notice is those intervals don't cover the full range. And that was based on that restriction and being able to calibrate the facility. However, the measurement intervals are present everywhere you see those 5 circles, which came from the plot. Those are the points we want to estimate roll torque. Now, if you quickly look at that plot, you can see there's a downward trend. And that's where we spent a lot of time from the beginning to the end. And it turned out that there was a sensor that was temperature sensitive that determined when we were at 0 degrees, when the nozzle was directly aligned. And that temperature sensitive component was calibrated such that it was about right in the middle of the firing. It was biased in one direction near the beginning when the engine was cool. It was biased in the other direction toward the end when the engine was hot. So there's a couple takeaways here. One, these prediction intervals were only provided where they were supported by data. Very important to deliver and a caveat on the delivery of the products. And we found this trend that we needed to talk about what to do with it. And we did through a multidisciplinary team of the facility experts and the subject matter experts for the vehicle. And so here's the final answer. On this plot, the box plot I have shown on the left under prior, all of the information that was in that column plot, the range of all the different estimates where we started. Where it says new, that box plot is the representative of those 5 circles that I just showed you on the previous plot. And after considering this known bias, we were able to come to a consensus to estimate that the internal roll torque was about -8 thousand inch-pounds, plus or minus 13. And just a rough interpretation of that, if you're familiar with statistics, is that interval covers 0, and therefore we really couldn't distinguish it different than 0. This provided a significant reduction in the original requirement for the program of 200. Now, this was an estimate based on one test of one rocket. I'm sure that our colleagues in the military experience this challenge all the time, as we do, with very small sample sizes That's one. That's the smallest sample size you can have. And being careful about what you quote and in what that variability represents. That's a within rocket, not a rocket to rocket variability. So as the bookend this, the flight test happened in October of 2009. On the picture on the left, it shows the roll reaction control system in that upper stage of the rocket. And during the flight, the reaction system was active. And during flight reconstruction, post-test, we confirmed that the roll to work was as predicted from the ground test. It was a very nice bookend to the project. I'm going to quickly read over a couple challenging statistical techniques that this included. Restricted randomization in a destructive, irreversible process. No pure replicates. Restricted factor combinations. I don't know how many people take a general DOE course and they find out that they need to randomize and they can't do all the factor combinations. And that sort of becomes a problem in whether I can apply this method. This basically had all of those restrictions. We had restrictions on the predicted model. We had to come up with a way to do inverse prediction with uncertainty. We had to interpret those and build a consensus estimate. My main takeaway on this slide is that you will not find this problem in any textbook. Much the same with all the problems, many of the problems that we work with that are of this size and large in scale. But how do we develop a way to approach it in a way that we could teach somebody? And that's really the point of statistical engineering. And I'll say a few more comments on that in another slide. So if we look at a summary, what were some important points? Well, the precise objectives were not well defined. That's a big focus in statistical engineering, and that was a big lesson learned here. This is a real case study, and there was challenges there. We did, in subsequent firings, get better precision of those objectives and answer those questions better. But earlier strategic involvement with an attitude toward asking a lot more questions, I think would have helped. Success was not based on a single tool, as I've emphasized a couple of times, and it required some integrating and extending of multiple methods. And yes, all of these methods, a lot of them I've talked about are regression and design of experiments, but I don't want you to walk away and say that's what statistical engineering is about. That's just what this particular example used. Changes in this complex of a process required leadership and demonstrated benefits. And we changed the normal process. This was not a one-time solution. So those critical features are collaboration, being synergistic about the way we used our tools and embedding it. It was application focused. And that's a very distinctive piece. Impact driven, we reduced the uncertainty. And more importantly, it broadened the influence of statistical thinking and methods. This is my last slide. As I think about where that led, it had obviously benefits to the project that I'm discussing. Reduced that roll reaction control system uncertainty. But more than that, it improved the recognition of a statistician's value as a leadership level part of the team. There were agency level awards, multiple ones for this project, and I had the privilege of receiving on behalf of the team, a team award from the NASA administrator and the NASA chief engineer. I'm not sure how many statisticians have stood in that position. I'm honored and humbled by that fact, but I think that recognized and elevated the types of tools and the approach, more importantly, the approach of how to solve these kinds of problems. It resulted in organizational changes at NASA to establish statistical engineering teams, and those have, that impact continues to this day. It resulted in subsequent work for about 5 years afterwards to develop and define additional rocket motor performance requirements using these techniques. And I think for me personally, this was a huge motivation for developing and focusing on the discipline of statistical engineering. I had somebody ask me one time, how would you teach someone to attack this problem? Well, certainly knowing design of experiments and response surface methodology was necessary, but not sufficient to solve the problem. And what were the critical skills necessary? You know, that's where the benefit of these case studies to go back and interrogate that, I think, are very important. Very multidisciplinary skills. That's what was critical. And lastly, I've had people ask, where do you find people with these skill sets? And that's my interest in having this academic and rigorous discipline developed, whether that's a course, whether that's a degree, whether that's a short course, whatever it is, in order to get people farther up that learning curve, which we all get through experience, but get them to accelerate that as they go forward. And with that, I'm going to close and put up this slide with collaborators. If you know anything about me, I'm all about collaboration, and I definitely want to recognize that this was a team effort.
Great, Pete. Thanks, Pete. So I think we have about 4 minutes before we will, I think heading to the break or closing this session. And so I see a couple of comments, questions in the chat. The first one, Pete, inverse prediction requires that your function is one-to-one. How did that work out?
Yeah, so that's a great technical question. And the answer is that this was a calibration of a device designed to measure these forces and moments. And what that means is that while it's 5-dimensional space, we pretty much know where to start. We have a very good idea about the dominant responses. So it's not just general in the sense of mapping an unknown response surface. And we take advantage of that through our iterative solution. Said another way, we have a really good first guess, and then we iterate that because it's a calibration type problem.
Thanks, Pete. The next question is from Christine. First of all, she says, thanks for a great talk. And do you have any suggestions about how to slow the team down at the beginning to get everyone to really make sure that you're answering the right question?
Yeah, that's a great question. And I'll give you a couple different answers. One, you have to be seen as value added in the beginning, meaning pestering people with questions is not a good idea. You have to genuinely want to know, and you have to genuinely step out of your comfort zone to ask those questions. And the team members, particularly those who are not used to working with somebody who's going to ask them those questions, have to be able to see that value in what you're going to bring to the table. One way I like to do it is just to pose sort of a hypothetical. Let's imagine we're at the end of this, and I deliver to you, and I'll just give this as an example, that the internal roll torque measured at these 5 positions, given this uncertainty, and I can't put the numbers in there, but I can frame the statement, would that be sufficient to answer the question? And if not, then we have a conversation about sort of, teasing out more of the details of what exactly it means to measure roll torque. So that's a technique I've used, but I think that it's a mindset, it's a willingness to ask those questions, to show that you're adding value, to be patient, to do your homework, that you have to come toward them most of the time in terms of these subject matter experts, not waiting for them to come towards you.
Great, Pete, thanks. So I think we have maybe one comment, or maybe you could comment. I don't know if you're familiar with it, Pete. So SIAM has a nice computational science and engineering graduate degree program that's interdisciplinary. That might be a good fit for adding this course. I don't know if you're familiar with it.
Yeah, that's great. I actually am not personally familiar with it, but I will take that as a note. We have had this course or a course in this area taught at Virginia Tech in the Industrial Engineering Department, Industrial Systems Engineering. So I think that it will naturally, as echo what Roger said, probably not be taught in statistics departments, although it could be. I don't want to leave out that. And I think that programs like what you're mentioning about, computational science and engineering, that those combinations would be a fruitful place for a course or this topic to be taught.
Great. And maybe let's take this one last question, if you don't mind, Pete, and then we will close out.
Okay.
From Francesco, again, thank you for the great presentation. Wondering what led to discover the temperature sensitivity during the experiment to measure the torque.
Yeah, that's a great question. So I showed you those 5 dots going as a linear trend. There was no other explanation for about a month. And that's what drove us to try to figure out why should that be. There was no physical explanation on why the rocket and the way in which it burns. And I would encourage people to, Google search it, you'll see how it burns. It burns from the core, from the inside out. It doesn't burn like a candle from one end to the other. And so there was really no reason why the roll torque should have changed. Well, let's say there wasn't a good justified reason. There was obviously some theories about that. And so that drove us to really dig into the measurement system and talk to the facility people, and that's how we found it. So persistence, lack of other explanation, and yeah, persistence, persistence, persistence.
All right, thanks, Pete. Thanks again for the great talk, and I want to thank all three of our speakers for a very good session today. And I wish you all a great afternoon and hope you enjoy the rest of your day and the other sessions.
Yes, thank you. I'll echo what Andy said. Thank you for this wonderful session. It was a great intro to statistical engineering and insightful case studies. So virtual round of applause for all of our speakers. And go check out ISEA's website and join and keep up with the latest research and talks.